So today I'll talk to you about diffractive computing, how we can actually engineer light-matter interaction to compute. So diffractive computing has three major applications. One of them is statistical inference. You build basically diffractive elements that are designed using deep learning. And as the light is propagating through these passive structures, they actually infer, and they can be used for statistical inference. Another very exciting aspect of diffractive computing is to build computational imaging systems that you can think of as a superset to lenses. And you can also think of a diffractive network as an inverse design solution to inverse design. So think of a black box that you want to design between an input and an output, and you can actually think of a solution to that need provided by diffractive networks that are task specific. This last element I won't talk as much, but you can find related work from our team on inverse design aspect of diffractive networks. So a diffractive network is composed of layers, thin layers of optical surfaces that are engineered at the wavelength of, at the scale of a wavelength. Half a wavelength features are filling each one of these diffractive layers. The colorful looking things, these are phase elements. Basically the color map here is representing the phase. So all those half a wavelength phase elements, let's say 100 by 100, 300 by 300, 1 million, let's say, phase elements, each of which is lambda over 2, they collectively work with the next layer and the next layer and the next layer. Think of 5 layers, successive layers, like a deck of cards. They're optimized to do something for us. And that optimization is done in a computer using standard deep learning, your favorite toolbox, let's say. And once you have come up with that design, we fabricate it, we manufacture that, and it becomes a passive all-optical computer. So inference is all-optical, but training is done in a computer. So what are some of the unique features of this kind of a scheme? First of all, if after you've printed, after you fabricate it, the inference is all optical, so using passive layers, so it's low power. Except the illumination light, you do not need power. You can literally actually compute by diffraction. It computes the solution that you want at the speed of light, so low latency. These are very thin elements. So in the visible part of the spectrum, think of this as a stamp, like maybe 50 microns, 100 microns, very thin optical elements. That means as within that picosecond time that light takes to from one end to the other end, you compute your solution. And these are scalable. You can fabricate larger and solve larger problems with these diffractive layers. So the mathematics behind this is actually based on the Huygens principle. So every one of these diffractive layers, they're composed of these individual elements that are fabricated, but you can think of each one of them as a source of a spherical wave. And the phase and or amplitude of these spherical waves are controlled by the design, which means the interference from one layer to the other layer is modulated by the transmissivity of these layers. So this part, you can think of a diffractive network as a coherent processor, so you can actually encode information in the amplitude and or phase of the incoming waves and process it. It's a coherent processor. This part is a linear system, ignoring nonlinearities at the surfaces, and this is an intensity detection here. You can think of this as a bunch of detectors, CMOS imagers, CCDs, or photodetectors that are acquiring basically the intensity of the beam. So that's essentially your solution or output plane. As I mentioned, once you design this using basically an optimization like deep learning, you come up with the phase and or amplitude of these diffractive layers, one layer after another layer, through error back propagation based on a certain loss function, depending on what you want to solve with these layers. But after that, the whole design is fixed and you fabricate it. For example, if you want to use these diffractive layers for optical classification of handwritten digits. This is after convergence. This is what you get. These are the phase patterns. This is the color bar here. And this is how those 5 layers are optimized together to reveal a certain phase pattern that actually can do all optical classification. And as I said, these are eventually fabricated. This is a fabricated diffractive network. You may be wondering, what is this? Like, this is a plastic material. It's 3D printed diffractive network. And everything that I'll experimentally show today has been tested at terahertz waves, a wavelength on the order of 0.7 millimeter. Those security scanners, every time you go through an airport security scanner, that's a terahertz imaging system. Plastic, like this, is transparent, so you can think of that as gloss for terahertz waves. That's what we selected for proof of concept testing. One thing that's beautiful about this framework is this. You can take all of these designs and shrink the dimensions with respect to the wavelength that you want to use. That will work as you desire. So shrink everything with respect to the wavelength, and the design remains the same. If you're kind of like still not sure what I'm talking about, I brought here with me a diffractive network that is composed of 3 layers. If you just touch it gently, you can see the surface roughness there, and that's actually the code that we've designed. You can pass this around just to give you a little bit more context of what I'm talking about. So this is a closed lookup of a diffractive network that is a classifier, and these are the individual diffractive features. Each one of those peaks and valleys, they are at lambda over 2. So we process all the traveling waves in air, and that's the reason why we have lambda over 2. Making it lambda over 4 wouldn't help us. That's essentially a diffraction-limited footprint. In the first design that I'll share with you, this diffractive network was trained as a classifier of handwritten digits, which means if you give me a new number 5, for example, if you shine coherent light like a laser light through this handwritten digit, most of the photons will be detected by this detector at the back end of the diffractive network that's assigned to handwritten digit 5. So this is not mode matching. These are newly written digits, so you're not memorizing. This is actually statistically inference to unknown digits. So as I mentioned, you can encode the information in amplitude and or phase. This is a coherent processor. Here we're using the amplitude channel, which means the handwritten digits are encoded with the transmission amplitude of the beam. So for example, if you give me a new handwritten digit 2 and shine light through it, the diffractive processor will route most of the photons to here at the back end of the network, which is assigned to class 2. So on and so forth. For example, for 4, if you shine light through this, it ends up here, which is the correct class. So a maximum score of these 10 detectors reveals all-optically what you have detected. You can also apply this to more complicated problems. This is another data set publicly available. This is fashion MNIST, which means it's also composed of thousands of examples of fashion products. Bags, sneakers, trousers, shoes, etc. And here we're encoding the objects in the phase channel, which means if I give you, for example, a new trouser, newly designed trouser, most of the photons go to the correct detector here that's assigned to trousers. This is a dress, same idea. This one is phase encoding. You can actually do both at the same time if you want. So these were examples where there's a certain loss function, and in the previous examples we use mean square error, which means there are 10 detectors, each one of which is representing a certain data class. We wanted the network to fill that active area of that detector uniformly, like a beautiful square hat. But for classification purposes, you can actually switch the training loss function to cross-entropy loss, and that actually changes the game. It outputs speckle-like patterns, but the same rule applies. Most of the photons irregularly fills the correct detector, so you can actually improve your classification accuracy with a better loss function for classification. Just to give you an idea, apple-to-apple comparison, for MNIST and fashion MNIST, respectively, you can achieve more than 98% classification accuracy with this kind of a scheme. For fashion MNIST, you can achieve more than 91% accuracy by different tricks to optimize the layer phase profiles of these layers that collectively classify test objects from these data sets. In fact, you can think of a diffractive processor as a universal linear transformer, which means if you have a certain input field of view, which has complex waves, let's say a total of n sub I pixels here represented, and if you want to transform that with a complex valued arbitrarily selected transformation matrix, the amplitude is shown here, random, and this is actually the phase randomly selected. You can design a diffractive processor to all-optically perform any arbitrary linear transformation. For that, the total number of diffractive features, we call them diffractive neurons, need to be NI/NO, which means the space bandwidth product of the input times the space bandwidth product of the output. That's the degrees of freedom that you need to put in these diffractive layers to achieve a perfect approximation with zero transformation error, 1 cosine similarity, and output field nicely matching what the desired transformation reveals. But there's something more here in the sense that you can actually steal the degrees of freedom from the system. For example, you can operate to the left of this NI/NO curve, in this range here, and still have a beautiful approximation. And one thing that is striking here is that if you give me a certain number of diffractive features, putting them one after another in a deeper architecture helps us approximate better. A good example of this is shown here. We're trying to approximate a certain linear transformation matrix randomly selected with a certain amplitude and phase profile as shown here. If you give me only 7.2 thousand diffractive features at lambda over 2 scale to optimize, this is the errors that I make. All-optical transformation error in the amplitude and phase. Not good, but not terrible. If in fact you steal more diffractive features, degrees of freedom from the system, and give me only 6.4 thousand diffractive features, and put them across 4 layers instead of 2, you actually approximate better. So there is a depth architecture in the sense that the model processor that we have from the input to the output gets easier to train and have a universal approximation power as you distribute these across one layer following another layer following another layer. This is actually an interesting feature of it. I can talk to you more about that. For classification, for linear transformations, that's the same gist. It likes to distribute these diffractive features in a deeper architecture as opposed to a wider architecture. And there's a physical intuition behind it that's related to actually diffraction of light. And I can talk to you more about that maybe in the Q&A. Even though diffractive networks, just like the one that you're seeing, that's an isotropic material. It doesn't have any polarization processing capability. It's just glass or plastic polymer. You can actually have diffractive networks also process polarization information of light and provide a universal polarization transformation. To do that, you can actually still rely on isotropic materials, as shown here, but in between, put an array of linear polarizers. This is non-trainable. These polarization planes, they're composed of polarizer arrays, just linear polarized at different angles. That's static. By learning the rest of the diffractive features and their phase profiles, you can actually embed within the same isotropic system 4 different transformations for 4 different combinations of polarization states. At the input, for example, x to 45 degree, you can embed a certain complex valued transformation matrix. For a different combination, another arbitrarily selected transformation matrix, so on and so forth. So you can actually multiplex based on input-output polarization states, different arbitrarily selected transformations, complex valued transformations, implemented at the same time without changing the material. For that, you need more diffractive features. For example, if you ignore polarization with an isotropic system, you need NI/NO diffractive features. If you have 4 of these polarization encoded systems, you have 4 times more. You need 4 times more diffractive features to make this multiplexed polarization multiplex transformation. So it's a linear transformation system, and you can actually embed polarization transformations despite the fact that these are isotropic materials. So after this brief intro, one of the, I think, most exciting aspects, in my opinion, about diffractive computing is diffractive visual computing, meaning that an input scene, think of a camera, already has the phase information, the amplitude information, the polarization information, the spectrum information right in front of you. And you don't need any pre-processing. You don't need to digitize it and act on it. Think of, for example, phase retrieval. That's actually a very complicated and costly process. You need to digitize and act on it with perhaps some GPUs to get the phase information of a coherent scene. These kinds of diffractive processors act on the phase directly at the speed of light or polarization information. And I think that feature is one of the most exciting aspects of diffractive computing. You don't need to actually pre-process information, vectorize it, etc., etc. Everything is given to you, and you can act on it at the speed of light. I'll give you some examples of how we're utilizing this feature to design some unique optical imaging machine vision systems. Here, we're designing a diffractive processor that's going to actually have a single aperture, single pixel, to do basically classification. So it's a single pixel machine vision system where this time we'll be illuminating with a broadband light source. And the special features of the objects, the classes of objects that we want to classify, will be encoded in basically spectrum of the output detected from a single detector. So every one of these wavelengths, one by one, will be assigned to one data class, which means from that single pixel aperture, we'll be looking at the spectrum at those 10 wavelengths, and the maximum of those intensity profiles from that single pixel will reveal the class score. So this is actually a space-to-spectral transformation for single pixel machine vision. Again, this is tested in terahertz part of the spectrum. These are the resulting diffractive phase layers that you fabricate. This is the output aperture where we detect this spectrum for these 10 wavelengths, each of which is assigned to a certain data class. These are, again, testing with objects never seen during the training before. It's showing generalization. If you have a new handwritten digit 0 at the output, you have this wavelength, the 1 millimeter wavelength, which is representing class 0, has the maximum number of photons from that single pixel aperture. Same idea with number 6. So you do actually classification with those 10 spectral class scores through a single pixel aperture. You can also build an image reconstruction network that takes this spectral class score coming from a single pixel to give you what you've imaged by doing image reconstruction. So basically some sort of a super resolution in the sense that you have only 10 numbers here, which gives us a way to kind of classify, but at the same time reconstruct it with a shallow electronic neural net to give you exactly, to see if the classification matches, for example, with the features of the reconstructed image. Perhaps that can help us correct our misclassifications coming from the diffractive network. These are some examples experimentally reconstructing the objects from just a spectral class score of 10 numbers coming from the diffractive network's output. We can encode more wavelengths into the system, so space-to-spectrum encoding can also include more wavelengths, just more than 10. Here we're doing actually 20 wavelengths where they differentially encode the information, which means 2 wavelengths differentially are assigned to each different class. So basically, this gives us the ability to represent negative numbers virtually, as opposed to having only intensity of the fields represent the class scores. That help us improve our classification and generalization, and the differential class scores coming from 2 wavelengths show here the advantage. You kind of have negative numbers for the unwanted classes, and the correct class gives you the positive polarity. With MNIST, with the single pixel spectral encoding, we have approximately 97% classification accuracy with the test data. And this is even more wavelengths used. Here we're looking into eMNIST handwritten letters, 26 classes, differentially encoded with 52 wavelengths, which means 2 of these wavelengths represent 1 handwritten letter. This is a class score coming from the differential operation, and you get something like 86% for handwritten letters coming from the single pixel system. These are some examples of statistical inference and how you can generalize to classify objects through this system. As I mentioned, one of the most exciting aspects of this framework is actually computational imaging. You can think of building smart cameras where the front end lens system is replaced with these diffractive layers for task-specific computing. And I'll start with some of the work that we've done on this domain by seeing through random diffusers. So here, the diffractive front end of a camera is charged with seeing through phase diffusers, where the object is unknown, it's completely hidden by a random phase diffuser, and you do not know the phase diffuser. In fact, it can change. So the rule of the game here is to design the phase profiles of these diffractive layers so that they take the modes that represent the phase diffuser and scatter them out, and whatever comes from the object plane is guided through the phase diffuser and the diffractive layers to form an image. So you will sacrifice some resolution, but still the goal is to stabilize the output plane despite object changing and the phase diffuser changing. Without any diffractive layers or without any smart imaging system, you cannot recognize the objects because of actually the phase diffuser. So the goal is to see through these phase diffusers. To be able to do that, we show a lot of examples of these phase diffusers during the training phase. So what we do is actually, at every epoch of this learning for the phase profiles of these diffractive layers, we show many phase diffusers. These are randomly generated phase variations that entirely obscure the information of the object. Through this process, let's say you have 100 epochs. At every epoch, you show maybe 20 of these examples. There you go. You have 20,000 of these random phase diffusers that distorted. And the diffractive networks are being penalized based on a loss function that has some structural correlation term, Pearson correlation term here, plus this capital E here, which is the energy efficiency, which means we want the solution to work with random diffusers, but at the same time, we want it to work with a certain efficiency so that I can count those photons and image the output. After the design phase, it should work with known diffusers. So K here, diffuser K1, K2, K3, these are known diffusers in the sense that these are used during the training phase. It should work, but it's not just the memory here. It's not the memory effect. You can also change the diffuser to new variations where it's not one of those that you use during the training. So B here refers to blind. Diffuser B1, B2, B3, they were never seen before. And these are test objects never seen before. So you have to have an imaging system that will work with known diffusers, no diffusers, and with blind diffusers. So these are some test examples where the network was only trained with MNIST, and now I'm testing it with gratings. So did it generalize to be a good imaging system to reveal basically the periods of these different gratings? So both for known diffusers and unknown diffusers, new diffusers, it works very well and tracks the resolution of these gratings, despite the fact that we never showed these kinds of objects like gratings to the network before. So it learned how to do general purpose imaging beyond just the MNIST handwritten digits. So you may be wondering, what is the physics behind this? How is this possible? How can we see through random diffusers? So I'll come to this in a minute. If you look at the layers that resulted, you see some beautiful pattern of phase islands surrounded by rapid oscillations from one layer to the next layer to the next layer. So these are the resulting diffractive layers. I'll come back to these layers and what they physically mean in a couple of minutes. But before then, I'll just switch to the experimental system. So this is the fabricated diffractive network, very thin, perhaps less than 100 lambda in total axial depth. In the visible, this is going to be, as I said, less than 100 microns. It's like a stamp. And it's tested in terahertz part of the spectrum, where we created various different kinds of test objects never seen by the network before. And we tested them with different kinds of diffusers, both known diffusers and new diffusers never seen before, and it works as expected. It's seeing through the unknown diffusers. Of course, terahertz part of the spectrum, imaging systems are in general more noisy, so there's some distortion in the edges, but still, you get the gist of the idea that the period nicely matches for these gratings that are tested. Same with the objects like 0, 2, 7. So this system works for as you change the diffuser, it's going to keep the image stabilized. Let's look at, for example, this row here, which is n equals 20. That means every epoch we use 20 random diffusers. 100 epochs, 2,000 diffusers were seen by the network before. So this is actually that competitive network that's trained. So it works nicely for both known and unknown diffusers. But if I take the diffuser entirely, as you can see, it also works beautifully well. So even if it never saw a case without a diffuser, it generalized to converge to a general purpose imaging system. It works without a diffuser. If you also change the diffuser statistics and make the grain size of the diffuser even smaller, like this one, for example, is a new diffuser, but with a different correlation length. It's much finer. So we never trained with those kinds of finer diffusers. We always work with this kind of a grain size. Even then, it actually performs a good imaging, despite the fact that it's actually a new diffuser with a different kind of statistical correlation length. So this movie highlights everything. You have new objects, unknown, new diffusers that are entirely blocking it. If you have a perfect imaging system, you get speckled patterns coming from the dynamically changing blind diffuser, and at the network output, all optically, you stabilize the image to see through diffusers. So how is this possible? To answer that question and to look at a little bit more on the physics of what's happening here, you need to understand what's going on with basically this kind of a diffractive autoencoder. So if I train a diffractive system composed of 5 layers without any diffusers, just to do image projection or imaging, this is the phase profile that you get for all of these layers. There is no diffuser here. If you zoom in, you see this dense grid of phase profiles. This is like every one of those phase islands here is a microlens, so to speak. So you have densely packed microlenses within each diffractive layer, and that's how you can actually mitigate diffraction between the 2 layers and project an object to the output. This is trained without diffusers. If you look at what we've converged with diffusers, it has the same characteristic. So if you look at the design of the diffractive layers when we train them to see through diffusers, you see the same microlens array from one layer to the next layer to the next layer. You have a self-aligned and self-assembled microlens array, but this time they're slightly separated from each other. So, in fact, if you look at the overlap of the axial positions of these microlenses, you can see a beautiful overlap, which means if you just look at the rays connecting one layer to the next layer to the next layer, these microlenses are overlapping axially. So they self-align, and that's the communication channel to actually provide imaging. But that's the general purpose imager. That's not the power to mitigate the diffuser. So each one of these microlens arrays, they're surrounded by rapid phase oscillations. And that's very important. It's the combination of the microlens array and the surrounding phase patterns that together provide imaging and mitigation of the phase diffuser signature. In fact, if you do some ablation study and erase the rapid oscillations and just keep the microlenses, as you can see, you cannot even image through known diffusers. You just get basically speckled pattern. So that means the microlens array here is important, but it cannot just mitigate the noise coming from the phase diffuser. But it's very important to do imaging, as you can see. Without any diffuser, it's the core imaging function, which means it's those high-frequency phase perturbations that take the modes of the phase diffuser, couple them outside to traveling waves that exceed the diffractive volume, and the combination of those high-frequency perturbations with the microlens array together give us the capability to see through random diffusers. We can also look at holography and phase retrieval and perform some more exotic tasks for basically all-optical diffractive network-based imaging systems. So here we're charging the diffractive network to do hologram reconstruction, but without a computer, all-optical. So imagine you have a plane that projects us holograms of objects, and the goal here is to project a beautiful phase-retrieved image that is the reconstruction of that hologram. So for this, the loss function is some spatial loss function, like mean absolute error and some Fourier transform related loss, mean square error in the Fourier space. And we also have a diffraction efficiency, because just like any other system, this is an all-optical processor, all-optical hologram reconstruction engine, but it must also preserve photons. So which means that diffraction efficiency is another knob that we play to make sure that the solution is also optically preserving some of the photons. These are some blind testing results. This is internal generalization, which means these are test objects from MNIST. These are the holograms, and this is the output of the diffractive layer. It also actually performs external generalization, which means you can take another data set that's never seen and apply it to the holograms of those objects never seen. For example, these are holograms that are projected onto the aperture of the diffractive layers, and this is the nice reconstruction, all optically revealing. So think of it as a display where you can actually project holograms where the reconstruction in front of your eye can come from a passive system without any computing power, because this is just glass that can reconstruct those and couple the twin image to the sides and get the real image focused to the output aperture. And this is showing you the trade-off between diffraction efficiency and the structural loss function. If you make this eta coefficient, which is in front of the diffraction efficiency, larger and larger, you get better diffraction efficiency at the output. For example, this solution is more than 25% at the output in terms of efficiency, but you sacrifice some quality of structural similarity index. So that's essentially the boundary of your solutions coming from diffractive networks. But still, with 27% accuracy, diffraction efficiency, you have still a beautiful image. So it's your engineering trade-off, so to speak. We can also do some more exotic transformations, like this one is phase to intensity transformation. So if I have a phase object, a thin object like a cell or a thin tissue sample, it's hard to image the phase information. That's why we invented holography, right? Decades ago. So, but what if we could actually use a diffractive network to do an approximation to take this phase object here and convert it into intensity in a quantitative manner, which means the intensity profile here is going to reflect the QPI, quantitative phase information of the object. So this is a network that does phase to intensity transformation, and while doing so, it preserves the quantitative nature of phase, which means the 0 to pi color bar here is going to be converted to quantitative intensity information at the output. So this one is also trained with a structural loss term, but here to make the solution independent of fluctuations of intensity, there's also a region here around the output plane that we use for normalization, which means if you shine more power, larger, let's say density of photons to the object or less, it doesn't matter. We do ratiometric analysis to give you the QPI information independent of the photon density at the phase plane. So this also shows beautiful, actually, generalization for both test objects of your training data set, or this was tiny ImageNet that we trained. Phase objects are shown here. These are thin phase objects which were converted into intensity at the output, revealing the 0 to pi dynamic range within the intensity of the CMOS imager at the back. And it also works, as I said, for other data sets, despite the fact that CFAR10 was not used in the training phase. These are some great things, also showing you that it's a beautiful imaging system, approximately diffraction limited, but not quite. One thing to understand is that just like any other physical imaging system, as I reduce the contrast of these phase gratings, you start to have some more noise. So which means everything's actually physical here. You have a diffraction limited phase to intensity converter while preserving the quantitative nature of phase imaging, QPI performance. Very much like holography, you also have a performance versus diffraction efficiency penalty, which means this is actually your trade-off. If you want to operate at very good image reconstruction, phase to intensity transformation, the diffraction efficiency goes down. If you want to increase it more than 10%, let's say, you have to live with some sacrifice in the approximation of the intensity for the phase features. To finish off, in the last 2 minutes or so, I'll finish off with a final example of some of the exotic transformations, especially when it comes to imaging systems that you can do. Here, the goal is to do class-specific diffractive imaging, to decide what to image, what not to image or not to image. So here we're building a class-specific camera where it's going to form a beautiful image of the input field for a target class. And for everything else, for all the other classes of objects, it's going to erase them all optically, so that the photons will actually scatter off, and the output will not get the photons of the structural content of the input for the undesired classes of objects. Here, the training is more exotic. You have a loss function that is panelizing the diffractive features here with two different sub-loss functions. The first one is understandable. It's an imaging system. Positive means the desired class, which means you have a structural loss term, PCC term, and mean square error that is making sure that the output for the correct class is structurally close to the target. So that's actually predictable. That's normal. That's kind of like expected for an imaging system. This negative loss is the one that is engineered as we failed and as it failed till it worked. So basically, this is composed of three subterms, the loss minus, which means this is the one that works to erase undesired objects without penalizing the forward model for the target class. It has actually, first of all, a structural loss term. We don't want the output to look like these. So that's the first beta 1 term here. It's the structural loss term between the ground truth that you want to erase and the input. That's kind of understandable. But the next two are, the terms that we put to make it work. It should also not hallucinate and turn some of these undesired objects into the target class. That's why we're also penalizing representative images from, for example, the target class, so that you cannot convert other other non-target objects into the target. So that's actually penalizing this transformation. Since this is a universal linear transform, it's very powerful. It can actually fool you in various different ways. You kind of need to stop them from fooling you. So that's the second exit that we were fooled initially, and then we closed it. And this is the third one, which is the diffractive network can also shift the input objects and fool your PCC, which means you need to also penalize shifted versions of the same non-target objects. Only after they come together, you can actually erase non-wanted objects and preserve wanted ones. You may be wondering, so what? Like, who cares for this kind of a transformation? Think of privacy-aware imaging. Every time you go through a security camera, you use terahertz waves to image your body. They don't care about your body features, but they reveal all the details with about 1 millimeter resolution if they want. But that's not what they're looking for. They're looking for metals, weapons. So imagine a system that can actually erase all of our body features, because that's not wanted, and only can reveal images as a photon flux when there is actually a metal object. So this is actually a great problem for class-specific diffractive cameras. These are some designs where 3 layers are working with phase signatures. These are the target objects. Class is 2. You create a nice image, and the rest, they're erased. You can also bundle and form a group of classes. For example, here, class 2, 5, 7 are bundled. You want to image them while erasing the rest. So you can actually create more exotic division of what is wanted, what is undesired. And it works for more complicated objects. This is actually a trouser imager, which means it generalized to image trousers. Think of an industrial application where you're packaging things. You want to understand if there is a defect somewhere, something is abnormal, the drug component is missing, or the active ingredient is not there. That's the only time that you want to image. The rest, you want to just let it pass. It's actually a similar scale problem. You here erase everything except one type of object. And this is a larger field of view showing you the class-specific imaging across the field of view. What was circulating actually is one of those diffractive designs. So what is inside that tiny diffractive computer was actually these 3 layers, layer 1, layer 2, layer 3. These are, again, for terahertz waves, 3D printed and forming a nice diffractive imaging system. These are some experimental results showing you for the correct class, forming a beautiful imaging system for the rest, erasing so that you can actually have a very weak and structurally dissimilar output for non-target classes of objects. I'll finish up with this one, which is on top of class-specific imaging, this is actually doing class-specific linear transformations. The previous examples, this matrix here was an identity matrix, so you were doing class-specific imaging, where we had an autoencoder that is class-specific. Here, we're also encrypting it, where we ask the diffractive network to be class-specific, but also have a linear transformation here. That is deterministic, so this is given to us. We learn this transformation here only and perform it all-optically only for one class, which means this is the encryption. At the decryption, if you have the inverse of that, you can recover the object. The rest are erased, no matter if you have access to T or not. So it's actually encryption plus class-specific imaging at the same time. So it's a class-specific linear transformation camera. So to sum up, to conclude, diffractive computing is a framework that you engineer light-matter interaction in a volume using deep learning. It can be used for statistical inference at the speed of light through passive light-matter interaction, so low latency, low power. It's also, I think, great for computational imaging, computational cameras, where the front end of the focal plane array, whatever way that you want to use, is a diffractive processor, a superset to lenses. And finally, it's, I think, very attractive for inverse design. A black box that can do certain input-output relationships much better than intuition-based designs. With this, I'd like to conclude, and thank you very much for having me here, and acknowledge here are the students, postdocs behind this work, and the funding agencies. Thank you.